Hey everyone, today we're talking about biochemistry and that's right, good old fashioned water, both of which are really important to biology class. So let's start with this question. Why the heck are we studying chemistry? Isn't there a whole class about chemistry? Isn't this biology? Yes, 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 yes. But when you think about it, chemistry is really the foundation of biology. So that means that if you look at any biological process, you can't deny that molecules and compounds and different elements are involved, which means you can't understand any biological process without understanding chemistry. We don't have to go into super great depth on chemistry, but there's some basics that are really going to help you this year. So, first, we're going to start talking about matter and atoms. Everything is made of matter. That's kind of true. Everything that is physical, like everything with mass is made of matter. But there are other things like energy, and obviously there are concepts like I don't know, love is a concept that's not made of matter. But we're going to restrict this to physical objects. Yes, those are made of matter. Matter is made up of atoms, and atoms are not the smallest thing that exists. There are things smaller than atoms. Those are called subatomic particles. And there are three of them that you can use to make up atoms. Protons are positive, electrons are negative, and neutrons are neutral, meaning they have no charge. So P for proton, P for positive. I like to think electrons are negative because if you get shocked by electricity, that would be a negative experience. And then neutrons are neutral or no charge. So easy to remember those. You also need to know where they live. So protons and neutrons are found in the nucleus of the atom. That's this dense central thing in the middle. And then electrons are found around the outside. Sometimes we draw them in these nice little neat circular orbits. Really, they're in this crazy cloud of buzzing electrons kind of all around the nucleus. And all this stuff gets tremendously more complicated if you study higher level chemistry or physics. Like there's even things that are smaller than protons and neutrons and even smaller particles like quarks and things like that. But we don't have to worry about that. Next, there's a really important point here. The number of protons in an element, the number of protons in an element's nucleus determines the element's identity or atomic number. So what's the difference between gold and lead and oxygen and hydrogen and nitrogen? The number of protons. What makes one element different from another is the number of protons. And we also call that the atomic number. So when you see all those numbers on the periodic table that go in order, 1, 2, 3, 4, 5, that's the atomic number. That's the number of protons. There's also a quantity we call the mass number, which is just the number of protons plus the number of neutrons, which is going to vary by different isotopes of the same element. And that's how we tell them apart, by their mass number. So atomic number, number of protons, the mass number, protons plus neutrons. Next, not everything in nature, not all matter is made up just of elements. Lots of things, most things are compounds, which means those are combinations of elements coming together to form chemical bonds to make more complicated things. Like glass, for example. Glass is not an element, it is a compound, silicon dioxide, which has silicon and two oxygen molecules bonded together. There are two ways that electrons can form chemical bonds. Both of those ways are basically an attempt to give those electrons a full outer shell or to give the elements a full outer shell of electrons. And the rules for that are the very inmost shell is full when it has 2 electrons, and then every shell beyond that is full when it has 8 electrons. Again, this is a simplified explanation. Once you take chemistry, you'll see things are a little more complicated than that. But our rule for this class is going to be the innermost shell is full when it has 2, and then shells beyond that are full when they have 8. There are different ways that electrons will be either shared between 2 atoms or transferred from one to another, but all of those different things are going to result in full outer electron shells. And that's basically how chemical bonds work. They're going to either share electrons, or one will gain and one will lose electrons until both atoms have a full outer shell. So you can see some of the examples here. Here are two hydrogen atoms. They're sharing electrons, so this shell can have two. That's the inner shell. Over here, this is an outer shell that you're looking at. And if they share these two electrons between the two, the outer shell of both of those atoms has 8 electrons. Similar thing with oxygen, except oxygen has to share 4 between the two of them to get that outer shell. This would be the other way of transferring. So if lithium loses an electron, then its innermost shell has 2. If that's the first shell, that counts as full. If it gives that electron away to this fluorine atom has 7 in the outer shell, so gaining 1 gives it 8. So that's the basic pattern that we're talking about. And because this is science, we have names for those processes. We don't just talk about sharing and gaining and losing. We call those chemical bonds, and there are 2 types of chemical bonds that you should definitely know. Ionic bonds happen when one atom gains electrons and another atom loses electrons. So that's like being transferred from one to the other. And covalent bonds happen when electrons are shared between 2 atoms. Within covalent bonds, there are 2 types of covalent bonds. One is a nonpolar covalent bond. That means electrons are shared evenly. Now that term is a little confusing because when you hear that non in nonpolar, it might make it sound like not equal. That's not true. Nonpolar is evenly shared between the 2. Polar means they are shared unevenly. I'll show you examples of those in a second. But before I do, I posted a link to this video in the notes folder. Definitely check it out. It is one of the greatest videos of all time. This is dogs teaching chemistry. These dogs know their chemistry. They're going to show you the difference between an ionic and a covalent bond, and they're going to be adorable when they do it. So you should totally check it out. This is one of my favorite videos. So yeah, that's in the folder. In a polar covalent bond, because the electrons are shared unevenly, that means one atom is pulling a little more strongly on those electrons, and one has a little weaker pull on those electrons, which makes one of those atoms positive and one of those atoms negative. Here's what I mean. On the left, we have a non-polar covalent bond. Remember, non-polar means even sharing. So if the 2 atoms that are sharing on those electrons, if they're the same type or a similar type of atom, they're going to pull evenly. So equal pull on the electrons means equal sharing, means there's no charge, right? So they're sharing the same. So they have the equal amount of charge on each other. In a polar covalent bond, remember polar is unequal sharing. One atom is a lot stronger than the other. And that's just based on the properties of the atom. That's something you'll learn about in chemistry. But for example, chlorine is really good at pulling on these electrons. Hydrogen is not so strong, which means that when they share, yes, they're still sharing, but chlorine has a stronger pull, so the electrons are a little closer to chlorine than they are to hydrogen, which means chlorine is going to be slightly negative and hydrogen is going to be slightly positive. And remember, that's because electrons have a charge. We said a couple slides ago that electrons have a negative charge. So if chlorine is pulling more strongly on those electrons, chlorine has a slightly negative charge because the negative electrons are closer to it. Hydrogen has a slightly positive charge because those negative electrons are far away. They're not spending much time next to hydrogen. So that's the difference between a polar and a non-polar covalent bond. I'll also point out that when you look at the periodic table, there are lots of elements. Most periodic tables you look at today are now going to be filled up all the way through 118. So these elements have names, which is a lot to keep track of. But in biology, yes, all the elements are important, but some of them are more important than others. That's why I highlighted some of these elements here, because really in biology, most of the time we're dealing with just a couple of them. And what do I mean by most of the time? Well, about 25 of those elements on the periodic table are essential for life, but 4 of those elements make up 96% of living matter. So carbon, oxygen, hydrogen, and nitrogen. Of the remaining 4%, most of that is phosphorus, sulfur, calcium, and potassium. So most of the chemistry that we're going to see this year is going to deal with these elements. When we start studying macromolecules like carbohydrates, lipids, proteins, nucleic acids, you'll see that they're made up of these 4. These are the big 4 right here. So that does kind of simplify things for you. Now we're going to take a look at water. So first of all, where can you find water on the periodic table? Let's see, I got a textbook here. Periodic table should be somewhere in here. Periodic table of the elements. Water is not on the periodic table because water is not an element. Water is a compound. That means it's made up of 2 or more elements that are bonded together. In this case, this compound is made of exactly 2 elements, hydrogen and oxygen. When they come together, you have water. So, rule number 1, water is not an element. It is a compound. All right, and water is also super important to biology. Life as we know it on this planet could not exist without water. That's why we are going to study it in so much detail. And let's see, I'm actually noticing a little typo here. And that's a good chance to talk about this. When you write the chemical structure for water, make sure you write it like this. That's a nice little teaching moment. It's okay not to be perfect, but fix your mistakes, I guess is the life lesson there. So when you write the chemical formula for water, it is H2O, like this. H in the O should be capitalized, and that is a letter O. It's not a 0. And then the 2 should be a subscript down here. So that means you have 2 hydrogens and 1 oxygen. So water is a polar molecule. That means it has a polar covalent bond, just like the type we talked about, which means the oxygen is pulling more strongly on the electrons. So if the electrons spend more time by the oxygen because it's stronger, oxygen is a little negative, and then the hydrogens are a little positive because of that unequal sharing. So you should know water has this characteristic Mickey Mouse type shape. You should know that the oxygen is in the middle, slightly negative, and then the ears, the hydrogens, are on the sides and they're slightly positive. Okay, this is a really big idea. Lots of the different properties of water we are about to talk about can be explained directly by what you see on the screen now. And these are a type of bond called hydrogen bonds. So hydrogen bonds form between water molecules. You can see them in the picture here represented by the dotted lines. So these are strong chemical bonds, but they are not the strongest type of bonds. The covalent bonds that hold the hydrogen and the oxygen together are stronger than the hydrogen bonds you see between molecules. That's why we're showing them as dotted lines, because they're not quite as strong. However, these hydrogen bonds are going to cause the different molecules of water to want to hold on to each other and be kind of sticky towards each other. And that is because the oxygen is a little negative and the hydrogens are a little positive, which means they're attracted to each other. So opposite charges attract. So these positive hydrogens are attracted to the negative oxygens. Same thing down here, same thing over here, which causes these positive negative attractions or hydrogen bonds to form between different molecules of water. They're usually shown with dotted lines like that. Like I said, the reason or the result of these hydrogen bonds between different water molecules explains lots of the different properties of water that we're going to talk about. Things like adhesion, cohesion, surface tension, capillary action. Anytime you have water sticking to itself or sticking to something else, it's probably because of these hydrogen bonds. So when we get to those properties, think hydrogen bonds. Okay, now we're going to go through and talk about a lot of the different properties of water, why they're important, why they happen, and in lots of cases, what they mean for biology. First is going to be cohesion, adhesion, and surface tension. So adhesion is the ability of water to stick to other substances. So this would be visible when you see water sticking to tree leaves or pine needles or other surfaces, when you see water sticking to a window or the side of the car, or when you look in a graduated cylinder and you can see that meniscus shape. All of those are adhesion, which is water sticking to another surface. Water sticking to the leaves here, water sticking to the surface, water sticking to the glass in the sides of the graduated cylinder. That is adhesion. Cohesion is the ability for water to stick to itself. So that's when you have water molecules attracted to each other through hydrogen bonds. That's what we just talked about. Cohesion can explain lots of the different properties of water. So you can see here, these are just hydrogen bonds. This picture, I wanted to point out that the covalent bonds between hydrogen and oxygen are shown as solid lines. The hydrogen bonds are shown as dotted lines. That's a way to remind you that the covalent bonds holding the molecule together are stronger. The hydrogen bonds are a little weaker, but they're still strong enough to make those molecules attracted to each other and want to kind of clump and stay together. And we call that cohesion. Cohesion in action gives us surface tension. Surface tension is just cohesion at the surface of a collection of water. And that means that if you have water in a glass or in a lake or in any kind of container, there's going to be a certain amount of tension on the surface. You're going to see this in one of the labs we're going to do next week or the week after. But it just means those molecules on the top are holding on to each other. It's a lot like this trust fall over here. You can think of each person in this picture as a water molecule on the surface of a glass of water, and then their arms going across are like hydrogen bonds. Hydrogen bonds by themselves are not too strong, but if you take a lot of those hydrogen bonds and you put them together, they can hold up a person who's falling. That's exactly what surface tension on top of water is. And you can see some pretty cool things with surface tension. That's how these insects, water striders and other insects that can go on the surface of the water, that's how they stay on the surface. They're not floating like a boat does. They are just so small and their feet are the right shape that they can stand on the surface without breaking the surface tension. And you can see that if you look closely, the surface of the water never breaks. You can see the surface actually bending down as their feet go on it. You can also see this with a paper clip. Hint, hint, that's going to be foreshadowing for the lab that we see. Okay, next, we got some more science vocab, hydrophobic and hydrophilic. Let's see what these words mean. So I love breaking words down into their pieces to see what they mean. Hydrophobic is hydro plus phobic. Hydro means water. Phobic means hating or fearing. So if you have like a phobia of something, you really don't like it. Hydrophobic molecules really don't like water. Things like detergent, wax paper, those are hydrophobic, means they do not bond well with water molecules and they tend to separate themselves from water. The opposite is hydrophilic. Hydro means water. Philic means loving. So hydrophilic molecules bond really well with water and tend to like water. When you take soap molecules are kind of confusing because they actually have two parts. They have a hydrophobic part. That's this long tail you see out here. They have a hydrophilic part, which is the head at the top of the molecule. When you take those soap molecules and you throw them in water, they dissolve and they spread out, and they actually break the surface tension by coming in between these water molecules at the surface and making it hard for them to form those hydrogen bonds between each other. These two water molecules usually would like to line up, so you have a hydrogen lined up with an oxygen, positive to a negative, to form a hydrogen bond, but the soap molecule gets in the way. So when you add even a little bit of soap to water, it makes it hard for those hydrogen bonds to form, which means you lose your surface tension. That's another thing that you're going to see in the lab next week or whenever. Hydrophobic and hydrophilic also explain experiments when you take oil and water and try to mix them together. So you can see even if you stir oil and water, they'll always separate out. That's because oil is hydrophobic. It doesn't dissolve in water. It doesn't like water. It doesn't bond with water. It'll separate out. Other compounds, like food coloring, are hydrophilic, meaning they like water. That's why when you drop food coloring in water and stir it, it'll mix evenly because it bonds well with those water molecules. Okay, the next characteristic is capillary action. And you can see capillary action with these nice multicolored celery, or if you have a tube or like a straw in a glass of water. Capillary action is just the tendency of water to go up narrow tubes or straws. And that's usually against gravity. That happens from two things working together, some cohesion and some adhesion. So it's adhesion because water is sticking to the sides of the container. And it's cohesion because the water molecules that are sticking to the side are pulling up other water molecules below them and sort of helping that process happen. So cohesion and adhesion together explain capillary action. This is another experiment you'll see in the lab. But if you take pieces of celery and you put them in colored water, celery has this vascular tissue. All plants have, well, not all plants, but celery is one of the plants that has vascular tissue that is like tiny little tubes. So when you stick them in the colored water, you will see over time, the water actually goes up those tubes, showing capillary action moving to the surface of celery. And if you leave the leaves on there, you can see it'll actually go all the way up to the leaves and give them nice little colors. Okay, next is universal solvent. Water is sometimes called the universal solvent, which means it's really good at dissolving stuff. Any drink that you've ever had is, well, hopefully something that's dissolved in water. When you buy a soda pop from the vending machine, most of what you're paying for is water with just some carbon dioxide and sugar and coloring mixed in. But all of that is just stuff that is dissolved in water. Water is called the universal solvent. Technically, it's not universal. It doesn't dissolve everything, but it's good at dissolving things, so that's where it got the term. So a great question that you're going to have to answer is, how do you know if two things are going to mix together? How do you know if water will or will not dissolve something? And a good rule is that like dissolves like. So what that means is polar compounds will dissolve polar compounds. Nonpolar will dissolve nonpolar. And if you mix one of each, they will not dissolve together. So like dissolves like, and you have to remember that water is polar. Like we said at the beginning of this, because of those polar covalent bonds, the unequal sharing of electrons, the positive and the negative, water is polar. So it is good at dissolving other polar compounds. So this is a summary. Polar will dissolve polar. Nonpolar will dissolve nonpolar. That's like dissolves like up here. And that just means if you mix two different ones together, a polar and a nonpolar, or a nonpolar and a polar, they will not dissolve. And this is the same example we saw earlier, oil and water. So this is oil and water not mixing together. The term we used to describe oil earlier was hydrophobic, because it doesn't like water. But now, because it doesn't dissolve in water, you could also use the term nonpolar. So if it dissolves in water, it's going to be like, because it's like dissolves like. So if it dissolves in water, it's going to be polar because water is polar. Love it. But if it doesn't, that means it's going to be nonpolar. So that example shows you that you can use the term nonpolar to mean hydrophobic. You can use the term polar to mean hydrophilic. That's really confusing. I know that's a lot. And without seeing an actual example, you still might be a little confused. You will see this example when we do the lab of all these different solutions that mix together or don't mix together, and this will help make that more clear. The next property of water is the density. So water is kind of unique because it is more dense as a liquid than it is as a solid. That's not common. Most things, when they freeze and they become a solid, become more dense and they'll tend to sink to the bottom. But water, due to those hydrogen bonds, becomes less dense when it forms a solid, which is ice. And because it's less dense, it floats to the surface. There are lots of important things that this causes in biology. So in one example, if you look at ponds in the winter, the coldest water becomes ice, floats to the surface, and so the surface of the pond will freeze. But that, even though it's ice, that a layer makes a barrier between the bottom of the pond and the top. So that actually prevents the rest of the water down below from freezing, which means fish and some amphibians and reptiles can actually live down there, and they would die if the water froze all the way down. That's also important for animals that live or use the ice, like cute little polar bears, because if ice didn't float on the surface, they couldn't use it to hunt. All right, next is the specific heat. So specific heat is probably another new vocab word that you might not have heard before. It's also something that you might learn a little bit more about in chemistry or physics class someday. But the important thing to remember is specific heat is not temperature. So specific heat is something different. It doesn't mean water is hot or cold. Water can be lots of different temperatures. But specific heat is the amount of energy you have to dump into a substance to heat it up. And when you look at water, due to the hydrogen bonds, those strong forces holding the molecules together, it takes a lot of energy to make water heat up, and more energy than it does other substances. So if you want to take water and raise its temperature by 5 degrees Celsius, it takes more energy to do that than if you're trying to heat up lots of other substances. That's what we mean when we say water has a high specific heat. It takes lots of energy to change its temperature. When water is phase changing, so either melting or freezing, or water is boiling or condensing to become a liquid again, the temperature is constant. You can see these in these two graphs that show temperature on the y-axis, heat on the x-axis, and these are phase changes. So if you look at the diagonals, you can see solid, liquid, and gas. Between those are the phase changes. So if we go from left to right, when you go from a solid to a liquid, that would be melting. When you go from a liquid to a gas, that will be boiling. And if you look at the length of this line, so here's ethanol. So that's a substance other than water. And here's water. You can see this line is a lot longer, which just means it takes a whole lot more heat to basically melt water from a solid to a liquid than it does to melt ethanol from a solid to a liquid. So that's just an example. This is something that you'll see a little bit more in the lab as well. But long story short, it takes a lot of energy to change the temperature of water. Let's see, you shall not pass. Stop old slides beyond this point. Dare you go no further. All right. Well, that's all I need to see. I don't think we're going to go any further because they're old slides. And you have already watched this whole video. Congratulations for making it to the end. I appreciate it. I'm not going to make you look at those old slides. So enjoy the rest of your day. And if you have any questions about these notes, please let me know. And I hope to see you soon.